Hello, everybody. Welcome to our seminar today. Today we have Fundamentals of Weathering, Part 6, Correlation. You made it almost to the end of our series on the fundamentals of weathering. And you might remember me if you attended all of our seminars from the first part of this series, Factors of Weathering. But for those who are new to this series, let me briefly introduce myself. My name is Florian Feil. I'm your presenter today. I'm working for Atlas Material Testing Technology as manager for our client education program and also as consultant for weathering technology. And also I'm representing Atlas in several standardization committees, ISO, but also at ASTM, DIN in Germany. Yeah, as you might recognize from my pronunciation, actually from Germany. And as you might see also with the camera, I don't see it currently myself, it's already relatively dark. So for me, it's definitely good evening, but we have attendees from mostly the Americas today, some from Europe actually. But so for you, it's a good day, good morning. And actually, because of that, I'm turning off now my camera, probably also because of a little bit of bandwidth at the end. It's a lot of internet traffic going on. And the important part is the slides I'm showing you today. And my background is actually chemistry, so I'm a chemist. And actually even polymer chemistry is my background. So I'm in many instances are very close to our customers of Atlas Material Testing Technology in regard to understanding what's happening to the materials. Yeah, just a little bit of housekeeping in the beginning. Everybody in the audience is muted, but you can submit your question via the question bar on the GoToWebinar control panel. Today's presentation, and I will try my best, should last about 55 minutes, and hopefully we have time at the end to go through all the questions. I will have an eye on the questions as they come in during the seminar and maybe answer them during the seminar, but I will definitely have a time slot at the end for answering the questions. And even though you have questions after the seminar, you can always contact us and ask your question related to correlation today, but also to the other topics related to weathering. And at the end of today's presentation, there's also a short feedback survey popping up when you close the GoToWebinar control bar, and we would be happy if you could answer those to help us to improve for future seminars. Yeah, us is Atlas Material Testing Technology. We are a global manufacturer of weathering test instruments. We also provide weathering testing as a service, outdoor weathering, laboratory weathering. So we have test laboratories in Mount Prospect, close to Chicago in the United States, and in Linsengericht, close to Frankfurt in Germany. And we also have Atlas Custom System, where we do larger scale solar simulation for wind tunnels, but also for crash tests, for example. And we do consulting, we do client education, and we are active in standardization. And that's actually mostly where I'm active at Atlas Material Testing Technology. And by providing this support, client education, standard support, consulting support, we hope we can support our customers globally and have a good relation to our customers globally. And that's why we spend all of these efforts in our client education program. And we hope you like our client education program. Yeah, you made it, as mentioned already, to the sixth part of the fundamentals of weathering. Today we will talk about correlation factors, different type of correlation factors, different type of statistics or approaching correlation, dealing with correlation, and we will go through some examples dealing with correlation. Yeah, correlation in weathering typically addresses the relationship between two tests or the performance of materials in two different test conditions, in two different test scenarios. And typically you compare a change of material in different setups. This can be artificial weathering, but this can all typically compared to natural weathering and environment which is close to the end use environment of the materials to be tested. And correlation is describing the relation between the two different test setups. But you can also do correlation studies between different type of instrument, different light sources, different instrument geometries, maybe also different instrument generations. So correlation addresses the relationship between different tests, the performance of materials, the property change of materials in different test scenarios. Yeah, but correlation is statistics, and yeah, with statistics it's always a little bit difficult, I would say. For statistics, it's important that the data you use for the evaluation for the statistics are relevant data. So relevant data means that the data has the same cause, the same influencing factor. So also the data are cause and effect. And just to give you an example from the real world, the real non-weathering world, I would say, we have the correlation between the outside temperature and the ice cream sales. And actually in Germany, and in Germany, we like ice cream, but only in summertime. So the higher the temperature, so more ice cream is sold. So cause and effect. And it's obviously a good correlation. However, correlation is statistics, and you can do a correlation with any type of data, either relevant or not relevant. And here we have the comparison over several years between the points of the lowest scoring team in the German Football League, which is hopefully not Eintracht Frankfurt, which is my team. And this shows actually a relatively similar pattern to the annual harvest of red cabbage in Germany. So, a good correlation statistically between the lowest scoring points of the lowest scoring team and their annual harvested red cabbage. Is this real correlation? Yes, it is. It's real correlation or pseudo correlation, but the data are not relevant. Again, correlation typically is a completely statistical evaluation of data and is not asking for the relevance of the data. So it's, and you typically, if you search long enough for fitting data sets, you find something which fits. And so you can do a correlation between, but the reason for the correlation is completely out of context. So correlation is just the quantitative, the statistic evaluation of data, the mathematical relationship between different test results in weathering. However, it's always important to also look at the relevance of the data. In weathering, for example, very often many materials have different pathways for yellowing, different mechanisms for yellowing. And you always have to check if the same root cause is causing the same effect. And therefore, it's very important. On the one side, you can do the correlation study, simple statistics, but the best way to approach correlation is you do an additional plausibility check to check if the data are relevant. This can be done with some analytical method like FTIR, carbonyl index, and so on. But typically, that's not done. Typically, in weathering, correlation is simply done on appearance changes like color change, yellowing, gloss loss, and so on. And the relevance is very often taken for granted, I would say. But if you want to do it 100% correct, you also have to always look at the relevance of the data. Which leads me to a first short poll I want to do today. And actually, I want to ask you which factors may have a negative effect on correlation. What do you think which factors have a negative effect on correlation? And actually, I'm launching it right now. And you can choose now between different answers. First of all, a short wavelength exposure below the natural UV cut-on can have a negative effect on correlation, or a spectral distribution with high deviation from solar radiation. High intensity, high irradiance testing can have a negative effect, or continuous exposure to light. So neglection of dark phases, relaxation phases, or unrealistic specimen temperatures. So high temperatures are likely to have a negative effect on correlation. So what do you think? I see questions coming in. Okay. So actually, it's relatively evenly distributed. What's coming in? Let me maybe 10 more seconds to collect the responses. I see a answer in the chat coming in. Okay. Okay. I close the poll, and actually I'm not very good in showing the results of the poll. Actually, can I share it? Yeah, I can share. So most of you voted for short wavelength exposure or unrealistic high specimen temperatures. And I must say, yes, you are right, but you are all right. All of these factors are actually known to decrease correlation, to have a negative effect on correlation. And I got a question, a comment coming in, which actually mentioned that it's all of them, and it's true, it's all of them. So all of these factors, all of these unrealistic, factors we're using, stress factors we're using, are likely or can decrease correlation. And even more, I did not list it all of them. And those factors are commonly known and already stated even in standards, like basic standards like ISO 4892-1 for plastics, or ASTM G151 basic weathering. These standards, they mention those factors which are known to decrease correlation, to have a negative effect on correlation, which are known to be unrealistic in testing. However, if you attended last week's seminar on acceleration, you might remember that these, especially the first 5 of these factors or influencing factors, are the factors which are actually used for acceleration, to speed up aging, to speed up testing. So, and this shows, in principle, as soon as you accelerate, you are likely to decrease, you may decrease the correlation. So you always have to find the balance between acceleration and correlation to get realistic results. But basically, the closer to nature, the more likely is that the results will correlate. But you lose, of course, acceleration. So it's always, again, a balance. Yeah, how to describe correlation in weathering. And there are some different approaches, I would say, in weathering to address correlation, to quantify correlation. And a very simple way to describe correlation, and we see this relatively frequently in weathering, also in weathering publication, is just do a correlation statement based on pass-fail criteria. And you probably also saw this example before, where Florida outer weathering for brown polyester coatings is compared to UVA weathering and UVB weathering. And for this test setup, the pass-fail criteria was a color change of delta E of 3 or greater. And actually, Florida weathering and UVA weathering, they have the same, or in those two scenarios, the same material passer tests. So coating number 1, 2, and so on, the ones on the left side, and coating number 9 and 8, they fail. In UVA, in outer Florida. So the same pass-fail criteria causes the same materials to fail and the same materials to pass the test conditions. So there is a correlation between UVA and Florida weathering. If you compare Florida weathering to UVB exposure, remember the last slide, short wavelength exposure, typically very unrealistic. And yeah, that's shown by the data here. Actually, it's the reverse order. The material which pass Florida, pass UVA, they fail in UVB, and the materials which fail in Florida and fail in UVA, they pass actually UVB testing. So a reversed correlation, I would say. But in general, there is no correlation between UVB and outdoor Florida weathering in general. That's a simple correlation based on pass-fail criteria, where some materials pass and some materials fail. But sometimes you even find publications claiming sometimes correlation where all materials actually pass the tests and no materials fail the test. There is one material shown here in the middle, which actually is below the pass-fail criteria in this study, but actually here the outdoor weathering counterpart was lost or not considered in the study, so this could not be considered in the study. In this example, ultra-durable powder coatings in a brownish red oxide color have been exposed, so different formulation have been exposed to Florida for 3 years and even longer, and to UVB weathering for 600 hours. So it's a very comprehensive study where this is taken from. And this was one of the few examples where a correlation was found, a good correlation was found between UVB testing and Florida testing, because all of the specimen passed the test. There was no failure. However, this is another example for correlation based on a simple pass-fail criteria, but here we don't have any differentiation between the different coatings. And in principle, there's no statement on causality and test sensitivity because the tests could not differentiate between the coatings. And as you might see by the residual gloss here, the ranking is completely different between the two test scenarios, but we come back to that later. But pass-fail criteria is very simple to do a statement on correlation based on pass-fail criteria, but you actually need materials which pass and need materials which fail to do a statement here. Otherwise, it becomes a little bit dubious, I would say. So it's better in general to do also statistics. And there are two commonly used statistics used in weathering. One is the Pearson correlation, one is the Spearman rank correlation, and we will go through both methods in the next slides and to look at examples of both methods in the next 40 minutes. Yeah, first of all, the Pearson correlation assigns a correlation coefficient which describes how good the correlation is. The Pearson correlation coefficient typically lies between -1 and +1. while +1 would be a perfect correlation, so identical data, and -1 would be a perfect negative correlation. 0 would be completely statistical data. And the Pearson formula, which is used to calculate actually the Pearson correlation coefficient, is shown here. And I've never calculated with this formula because this formula is actually embedded in MS Excel, and we will look at that also later, how to use MS Excel to calculate the Pearson correlation coefficient. But first of all, you need data to do a correlation. And as mentioned in the beginning, for a simple correlation study, you need data from at least 2 data sets, so from 2 test setups. And you need also different criteria for the data for the evaluation methods. So in weathering, you look at a set of materials, typically in a test scenario and a test method. And in this example, we have 3 different materials, material 1, materials X, and material N, in a typical weathering test where we look at the gloss loss during the exposure. And you either can test to a specified degree of property change. This can be the pass-fail criteria, for example, 50% of residual gloss. That would mark the end of your test setup. And this would be your evaluation or your test criteria. And the next step is what differs the different specimen to reach this gloss loss. And that's either the radiant exposure, that's better, or sometimes also the test duration can be used to reach that time. And that would be your evaluation criteria. So aging criteria, the time it takes, or the radiant exposure to get to a specific property change, in evaluation criteria is the time or the radiant exposure at this stage. Or you can do it another way, and that's what we most commonly see in weathering. You test until you get to a specific radiant exposure or for a specific time, and you do a correlation at the end of the test duration, the time it takes to reach the specific radiant exposure. And then you can do a correlation with the gloss at that time for as evaluation criteria. And actually, the best way to approach correlation, to select data for correlation, is you do a continuous exposure, have a continuous recording of the gloss over the full exposure time, and then you pick the time where you have the biggest differentiation between the different data. You can do a simple standard deviation, and where you have the maximum standard deviation between the different data points, that's the best time to actually do a correlation study. This shows the biggest difference between the different test materials. It's the highest efforts method C, but it's probably the best way to approach correlation. However, again, typically it's done more simple. You test until you get to a specific gloss, and then you do an evaluation of the time it takes to get to the gloss, or the radiant exposure do you take to the specific gloss change, or you typically also exposed to a specific radiant exposure, and then you just do a correlation study at the end point of that exposure. That's commonly done. But again, better to see the biggest differences. However, also in our example here, we use method A. So we expose in 2 test scenarios, test 1 and test 2, 3 different materials, the same materials, of course, in both test setups. And we do the exposure until we get to a residual gloss of 50%. And then we do an evaluation with evaluation criteria, the radiant exposure it takes to get to that specific loss for the different materials. And then we can simply do a correlation between the free materials, and we can calculate actually the Pearson correlation coefficient. Again, we come back to that later in more detail, and it shows an almost perfect correlation. However, here we have 3 data points only. And yeah, it would be even easier with 2 data points to just draw a line between the data and you get, yeah, a good correlation. So, and that leads me to the next poll. How many different materials you think you actually do you need for a correlation study? Let me launch the poll. Yeah. So what do you think? Do you need at least 3 materials, like in the example, or do you need at least 5 materials, at least 7 materials, or the more the better, or at least 5, but no more than 20, because when it's getting too much sets of materials, it becomes too complicated, and it's more likely that there are outliers. Too complicated, maybe better to stay with less. Okay, I see answers coming in. Maybe 10 more seconds. I actually see how many percent voted, so I maybe allow 10 more seconds too. Okay, let me close the poll and let me share the results. Yeah, so we have the more the better leading, and second at least 3, and next comes at least 5. So yeah, I think here in this case, not all answers are correct, I would say, but all answers have some motivation. In principle, let me hide this and go to the next slide. What's important is the data uncertainty, and in statistics to Pearson, you can calculate the uncertainty based on the pairs you can vary. And with only 3 test specimens, which you compare in 2 test scenarios, the uncertainty is relatively high. So if you calculate, for example, a Pearson correlation coefficient of 0.7, the uncertainty is plus minus 3. So the variability is actually between 0.4 and 1. So 3 is definitely not enough to do a correlation study. The uncertainty is just too high. If you have more specimen, the uncertainty decreases. So if you have at least 5 specimen, the uncertainty is plus minus 0.04, and that's, I would say, an acceptable uncertainty. It's not perfect, but it's an acceptable uncertainty. And the higher the number, the lower the uncertainty. And so in principle, the answer, the more the better, is correct. However, with limitations. And the more the better, the more data you have, the more reliable statistics. However, it's also more likely that the correlation coefficient is maybe not close to 1, maybe close to 0.7. And if you have a high amount of data, this can still be a very good correlation. So it depends, although it's not a the Pearson correlation coefficient, it's not just a number. You also have to look at the data and consider how many data are actually the basis for this Pearson correlation coefficient. We saw the example with the 3 data points and a good correlation, and here we have different distributions on data with a Pearson correlation coefficient of 1, where all data are identical, perfect correlation, and correlation coefficient of 9.8. Actually, you see it's actually relatively spread it out already, but still I would consider a excellent, almost perfect correlation. 0.9 spread it out even wider, but still very good, and so on to completely statistical. A lot of data means very often that the correlation coefficient of 0.7 or so still means a relatively good correlation. So a high number of data typically is better, but you need to accept a lower correlation coefficient with a very high number of data. And now coming back, how to really calculate the Pearson correlation coefficient, what you need actually. So you need data sets from 2 exposures. And here we have a set of some automotive textiles, interior textiles, which have been evaluated according to the color change, delta E. And there was a Florida exposure behind window glass for 12 different materials. And after 1 year, the color change was evaluated. And the same was done in a xenon arc test instrument after 100 hours, after 500 hours, and after 1,000 hours. And so you have the names of the test specimen, the names of the textiles, and the recorded color change in both test setups. That's all you need for a Pearson correlation. And in Excel, it's relatively easy. You just have to type in that in a cell that it's equal to Pearson. Then you have to include the first data set. So here from Florida, 16.8 to 3.8. So cell C11 to C22. Followed by the second set of data. And that's in this example here, the lab weathering results after 100 hours from D11 to D22. And then you just have to close the equation, press enter, and the program is automatically calculating the Pearson correlation coefficient. And it's 0.45, so not a really good correlation, I would say. Some tendency maybe, but not a good correlation. But you can actually do the same calculation after 500 hours. It gets a little bit better. And you can do the same calculation after 1,000 hours in the instrument. And it's actually 0.85. I would consider a really, that's a good correlation for 12 materials. So there is correlation between 1 year Florida and lab weathering after 1,000 hours. However, as mentioned, this is just a simple value. It's always recommended to also always look at the distribution of the data. Do a plot of the data and compare how the data actually align. And in this example, we see, it's relatively spread out, but overall, there is a clear linear tendency between the data. So this can be considered a realistic Pearson correlation coefficient. Why I'm mentioning this? Because with Pearson, you have to be very careful, because Pearson works only with normally distributed data. As soon as you have some order in the data, you can calculate, but the meaning of a Pearson correlation coefficient is not, it's not really meaningful. So it's here we have 4 different examples. In A, similar to the example we just calculated, I think it's 11 data points, or yeah, they're relatively normally distributed. That would be a typical Pearson suitable data set. In B, we have some order. I have no idea what's the background behind this scenario, but in Z, we have perfect correlated data and 1 outlier. And in D, that's very interesting. That's sometimes something we sometimes see in weathering. We have 1 test which can actually differentiate between different setup materials, and another test where all materials are actually behaving exactly the same, and 1 outlier. And the critical part here, if you just do statistics and do a Pearson correlation coefficient calculations, all of these data sets I'm showing here have exactly the same Pearson correlation coefficient. And actually, it would only work for the normally distributed data. So be careful with Pearson correlation. And Pearson correlation works best when you have similar materials which react similar to the test conditions in both tests to get a normally distributed data test set. And also, it's also very important that you have similar sensitivity. So do not include extremely sensitive or unsensitive materials, because that would definitely spread out the data distribution and cause some linearity, which might not be realistic. So similar materials with similar sensitivities and normally distributed data typically gives the most meaningful correlation results. Yeah, let's go into some examples. Some are relatively historic, but again, statistics do not change, do not need to be updated. It's just to visualization to give you some examples on how to use and how to manipulate also a little bit Pearson and later Spearman correlation. Yeah, here we have a example where automotive fabrics in different colors, different dyes have been tested. And actually 2 different types of automotive fabrics have been dyed in 31 different colors in with different dispersed dyes in 4 different colors actually. And also an additional material was considered in the study, which was identical to material B, but with a foam backing. So 3 types of fabrics, A, B, and C, and each in 31 different dispersed dyes. And those have been exposed to artificial and natural weathering, and the evaluation criteria was the color change after a specific radiant exposure. So here we have the exposure conditions, just more for your reference. So in black box under glass, outdoor exposure was done with controlled temperature, so where the temperature was prevented from overheating, and set to 95 degrees during the daytime, during the exposure time. And also a artificial setup, a xenon arc test setup was chosen, which uses a high irradiance, about 3 times higher irradiance than the typical irradiance level we use in artificial weathering, and also at relatively high temperatures. So 1 exposure conditions using the natural sun, and 1 exposure conditions using artificial solar radiation. And the test has been done up to a specific radiant exposure with intermediate evaluations, of course. And here we have the results from the outdoor exposure. So we see color change for two dyes, two fabrics, two dyes for all of the fabrics, and we see a relatively linear fading in the outdoor exposure. And yeah, also in the xenon arc exposure, we see a similar actually behavior after the different exposure periods. And the next is to do a plot of all the test specimen of all the 93 formulations, different specimen which are considered in the study, and we do a Pearson correlation coefficient calculation of all of those data. And overall, the Pearson correlation coefficient is 0.52, which is not necessarily a good correlation. However, if you look at the data sets for the different materials colored in different colors, you see that the different materials are actually behaving a little bit more linear than the overall setup. And so material A and B, different chemistry maybe, so it might make sense to do a separate correlation between the two of those. And material B and C, again, the same fabric, but C with a foam backing. And a foam backing causes higher temperatures. And there might be a slight difference between the two test setups. Typically, xenon arc exposures are continuously at the maximum temperature, so very hot, always the same amount of irradiance. So, and while in a realistic, more realistic outdoor exposure, you have maybe the continuous of 95 degrees, but you have less irradiance in the daytime, in the morning and the evening. So there might be a systematic difference between B and C. So it makes sense to separate the two sets also. And if you do actually a evaluation of all the independent fabrics, you get much better correlation coefficients. So because the test specimen behaves differently to the stress factors, so it's appropriate to several correlations and to avoid a general correlation in that sense. So there is a very good correlation for all of those. They are not perfect in all cases, but only for the individual fabrics, but not for all fabrics together. So, and that's a general guidance. If you compare a huge set of data, different materials, different polymers, different fabrics, different fibers, different type of coatings, sometimes you find the overall correlation maybe a little bit, not non-perfect, but if you do it either by polymer type or maybe by color, you might get a better correlation for the individual groups you can for. And that's always also very helpful if you have huge amount of data. A very comprehensive correlation study was done also several years ago by Dr. Scott Crump. And at that time, Dr. Scott Crump was director of a company called Co-Composites, and they actually acquired a lot of different gel coating companies, and all of those gel coat companies had their specific individual test method. And they once and for all wanted to find out which test method gives actually the best correlation to Florida outdoor weathering. And we did a very comprehensive study on gel coats in 10 different formulations, and each formulation in 3 colors, so red, white, and blue, probably an American study. And so 30 different specimens, and we looked at several different exposure methods, and they were looking continuously after specific steps at the color change and the loss of those specimens. They looked at Florida outdoor weathering, that's the reference. They looked at UVB weathering, UVA, carbon arc weathering, and different type of xenon instruments, a larger xenon instrument, CI barometer in this example, and a small xenon instrument, sun test CPS was used, so with a relatively limited control. And we included also natural accelerated testing in the comparison. So the EMAQUA devices, the solar concentrator devices with nighttime spraying have also been used in the study. And overall, they did a evaluation on the gloss, on the color change of all of the specimen. And the question was, which of those test scenarios gives the best correlation to Florida weathering? And overall, looking at the gloss and the color change, UVB did not show good correlation. UVA a little bit better. Carbon arc also not a very good correlation, especially when it comes to gloss. Maybe a little bit better when it comes to color change. Xenon arc devices, the smaller xenon arc device with limited temperature control, limited humidity control, really in the middle range. For the larger xenon barometer in that example showed the best results actually of the artificial methods. And overall, the best results actually could be achieved with the EMAQUA, with the solar concentrators. Not for white. The white color change showed a little bit discoloration, which was a little bit off, but the other colors showed the best color change. Yeah, we did also a cross correlation between the different methods, but I don't want to go into detail here. So overall, and you probably saw the slide also in the acceleration presentation, based on these statistical methods, they found out that they can get a balance between acceleration and correlation by mostly realistically simulating the weathering appearance, the weathering effects. So realistic sunlight, realistic temperatures, controlled temperatures in artificial weathering gives the best correlation and also an acceptable acceleration. So the more realistic, the more likely it will correlate. Yeah, however, not all materials behave the same. Not all materials behave linearly. So typically what's happening, and that's actually happen very often, is that the ranking is changing during the exposure. Here we have a -2 would be the corresponding standard today. And they saw that in this set of coatings, the delta E is actually changing the ranking during the exposure of 3,000 hours. So in the beginning, the green material C, it was not really a green material, it's just shown here as green. Material C shows the fastest aging, but then the color change is decreasing. Material A is almost linearly decreasing, D is linearly decreasing. B is the best in the beginning, but then suddenly the fading, the color change is actually increasing. So the ranking is changing continuously in the exposure. And the best time for comparison actually to Florida in this example would be for the instrument exposure after 2,320 hours, where we have the same, almost the same ranking as in the Florida exposure. So it's important to know when you have the best ranking between different exposures. And that where Spearman correlation comes into play. And Spearman correlation, it's actually relatively similar like Pearson correlation. It assigns a correlation factor, a correlation coefficient. And again, this would be 1 when it's perfect correlation and 0 when the data are completely statistical. And Spearman is mostly useful to find the best time to compare different data sets. And the formula which is used to calculate the Spearman rank correlation, is unfortunately not embedded in MS Excel. So you have to actually calculate the Spearman rank correlation coefficient yourself. However, you only have two variables. You have n as the number of pairs, and you have d, the different ranking, and the sum of all the different rankings squared. And that's all you need to calculate the Spearman rank correlation coefficient. But we will go through that with an example and also a data calculation based on 6 coatings where the gloss was evaluated. And here we see the aging in a xenon arc exposure for 1,400 hours with intermediate evaluation each 200 hours. And the question is, when do we get the best correlation to Florida weathering to 1 year Florida? And we start with the evaluation for 400 hours in the instrument. And for both scenarios, like for Pearson, we need the evaluation criteria, which is the gloss after the exposure. We have the gloss here for material A, B to F after 1 year Florida and after 400 hours in the instrument. And then you simply have to assign a ranking from the best, which would be material D in Florida, second best, material E, third, material A, and so on. And you do the same ranking for the device exposure. Here you see it's a different ranking. And the next step, according to the Spearman correlation formula, is you have to calculate the difference in D. It does not matter which way you make it, which way you calculate the difference, because then you have to calculate the square out of it and sum up all of the squared differences. And that's this part of the Spearman correlation formula. Then you have N. N is the number of specimens, the number of materials you have in the study, which is 6. And actually, it's a bad example because this 6 shown here in the formula is part of the formula, is not related to the number of pairs. It's always a 6, no matter if you have 10 or 20 specimen under consideration. And that's all. Then you can simply calculate the Spearman correlation coefficient, and it's actually after 400 hours, the Spearman correlation is minus 4.43. So it's actually more or less bad negative correlation. So definitely not the best time to compare it to Florida weathering. However, you have other data sets, you have 600 hours, 800 hours, and you see the ranking is changing. So you can do the same calculation for each of those exposures, just assign the ranking and do the calculation of the Spearman correlation coefficient. And then you see after 1,000 hours in the instrument, you get a Spearman rank correlation coefficient of 0.8. You don't see it, but it's 0.8, around 0.8. Then it's dropping again. So, and that would be the best time to compare Florida outdoor weathering to the artificial weathering, to the xenon arc exposure. 1,000 hours in the instrument and 1 year Florida show the best comparable ranking of the materials. Yeah, we have another example. I will not go into detail here. It's very similar. Specimens are exposed to a specific, until they achieve a specific color change in Arizona and in artificial weathering. And then the evaluation criteria was the time it takes to get to the specific color change, and then the ranking was assigned. You get this in your materials. Yeah, another correlation study on ranking of different materials is done here. A very small setup, only 4 materials, 2 printing inks in two colors, so 4 materials overall. I just showing this to you because Spearman has another benefit over Pearson because it can use different evaluation criteria for the statistics. And here in an outdoor exposure, those 4 printing inks have been exposed until a color change of 30 was achieved. In the device, the color change was measured after 48 hours of exposure. So completely different approach in both test scenarios. But if you assign just a ranking from the exposures and a fluorescent UVB exposure was done here, a xenon arc exposure was done here, a UVA exposure was done here, and a Arizona and a Florida exposure, you can simply assign rankings, and based on the rankings, you can actually calculate the Spearman rank correlation coefficient, even though you have different evaluation criteria. But briefly coming back to the example I showed you in the beginning, the example showing good correlation between UVB weathering and Florida weathering, yeah, done regularly based on pass-fail criteria. However, with Spearman, you can easily assign a ranking from the best performing in the one exposure to the worst performing in the other exposure. You can just number it by the residual gloss, and then you can calculate the difference in the ranking, the square in the difference, and you can easily, even without knowing the absolute data, you can do a Spearman rank correlation. And actually, Spearman says, based on the ranking, it's a very poor correlation, which is shown here. So no correlation between Florida weathering and UVB weathering, just based on the way to approach correlation. So it's very important, if you talk about correlation, you know which statistic was used to determine the correlation coefficient, because this also has an influence on the evaluation. What's better to use, Spearman or Pearson or both? As mentioned in the beginning, Pearson works for normally distributed data. As soon as you have outliers, it's completely screwing up everything, while Spearman is not so sensitive to outliers. And typically, Spearman correlation coefficient is bigger compared to Pearson correlation coefficient. If that's not the case, then you don't have a monotonic correlation anymore. It does not preserve the given order anymore. And then typically something's wrong, or something's off, and something has to be considered if the Pearson correlation coefficient is bigger compared to the Spearman correlation coefficient. In this example, we have here on the right side a perfect correlation, on the left side statistical data, and actually on the right side is the same data and one outlier, which makes it to a linear correlation, but it's not a real linear. It's only linear because of the outlier. Yeah, so you have to sometimes select the data by the sensitivities of the materials, especially if you consider color change. Color change is different for each polymer. It's different for each color. So, and here, just an theoretic example for polycarbonates and polypropylanes. Both can show yellowing, but the root cause for yellowing can be different. The sensitivities in different tests can be different. However, if you do a correlation overall, you get a perfect correlation because the data sets are far away from each other. And if you even consider a completely different material, PVC, different causes leading to yellowing, you get a completely off correlation by the different groups. So if you do a correlation by material, you might not get the best correlation coefficient, but you get a realistic correlation coefficient for the individual group. And here's also an example for wood plastic composites from a federal funded research project in Germany from the Fraunhofer Institute for Wood Research. And they looked at different formulations of wood plastic composites with different amount of stabilizers. And it was relatively interesting that they found overall a good correlation between an xenon arc test according to ISO 4892 2 and outdoor weathering in Braunschweig in Germany. And however, the correlation is only good because if you consider all of the materials, they behave completely different. Polyethylene is much more stable in this study, shows less color change compared to PVC, compared to polypropylene. And so just because you have completely different materials, it shows good correlation. If you look at the individual materials, yeah, I would say the correlation is actually relatively limited to, yeah, completely statistical. And if you look at the numbers of the stabilizer content in the different formulations, it's surprisingly that it's not actually, yeah, depending on the amount of stabilizers used. So it's relatively sensitive here. So it's, yeah, not the best to do a correlation study for all of those materials. And it's, yeah, no real statement can be made here on the overall correlation in this study. Yeah, correlation is on data selection. Correlation is statistics. And Winston Churchill once said, the only statistic you can trust are the ones you have falsified yourself. And the same is true for correlation. You need to somehow look at the data and in the worst case, manipulate the data if you have reasons for this. So reasons for manipulation, for selection of data can be you have different type of materials, maybe different colors. So you do correlation only for the specific type of materials, or you have materials which behave differently to different specific stress factors. So thicker specimen, for example, show higher temperatures because of the insulation, and that's a general tendency of thicker specimen. You might separate thick specimen from thin specimen and do the correlation separately. And you can remove outliers if they really screw up, and you can, yeah, either explain or not completely explain it. But if we screw up everything, you have to include them in the report. But for the correlation, it's sometimes advisable to remove the outliers. Yeah, one final example. So far, we have correlated different exposures, materials in different exposures. However, it might not necessarily be appropriate. Typically, a correlation factor is similar like an acceleration factor. It's related to a specific property change. So there can be, for example, good correlation related to color change, but bad correlation related to gloss loss. So a correlation factor corresponds to the set of materials and to the specific property change of the set of materials. However, there can be cases where different property changes have a realistic correlation with each other. And that's the case when you have the cause of a property change and the results of the property change correlated to each other. For example, the residual strength of a typical polymer film is decreasing with continuous exposure. And simultaneously, the oxidation rate, the carbonyl index, is increasing with the exposure. Oxidation means the transition, so the oxidation is actually the root cause for the reduction of the tensile strength. So, therefore, here there can be really a real correlation with relevant data between the different properties, carbonyl index by FTIR, and tensile strength between the polymers. So, and that's principally a realistic correlation which can be done here. And over a wide range of different polymers in a study, we was found that there's a good correlation, a good negative correlation, because the higher the Spearman rank correlate, the higher the carbonyl index, the less the residual strength, the less the elongation at break. And this was evaluated by Spearman and showed, again, almost perfect negative Pearson correlation coefficient, Spearman correlation coefficient for a huge amount of different types of polypropylene formulations. So causality is given, and the good thing is here, a destructive criteria like elongation at break can be replaced by a non-destructive method, the carbonyl index. Yeah, again, to summarize, a compromise must be made between correlation and acceleration. The closer to nature, typically, the more likely it will correlate. You have to consider the test conditions related to the specific sensitivities of the materials. Generally, the more you know about the aging of the materials, the better you find the easier you find the balance between correlation and acceleration. Correlation factors are best done using the statistical methods, and in principle, you always need sensitive materials which show some sensitivity that you really know that the test conditions cause effects on the materials. In general, test recommendations for correlation studies and for many weathering results now at the end of weathering testing, now at the end of the series. In principle, for weathering testing and especially for correlation studies, it's always advisable to include materials you know, control or reference material. And always also it is recommended to include materials which will fail, which will show the test actually causes effects to the materials. And for correlation studies, use at least 5 different material sets in different exposures. The more, the better. Use similar materials or groups of similar materials for the study. So same polymer, similar formulations, maybe similar amount of stabilizers, similar color, so that it's not linearly spreading out by the setup of the study already. Plan generous in the amount of specimen you're preparing. It's always good to have some as backup if you want to do additional correlation studies in the future and still have test specimen. It's much better than have new formulation. Then you in principle have to restart everything again. Do intermediate evaluations. So this gives you the development of the aging, maybe a change in ranking from time to time. And you can be sure that you do not miss the point of time where we have the maximum differentiation between the different type of materials. And yeah, use at least 2 different test methods for correlation studies, but you can easily use more and in a more general correlation studies. And from each comparison, you learn something about the performance of your materials and the reliability of your study. And yeah, in the end, correlation study takes a lot of time, but it in the end gives you confidence in your test method if you know how it correlates to your material, to your product and the real world performance. And if you start with a new formulation and you develop a new product and you already know on your test conditions, on your test method, how the correlation is, this gives you much more confidence in the performance of your product than it would be without a appropriate correlation study. Yeah, that's it from my side. You probably saw that slide already where you find us or find our information on our homepage. And yeah, with that, that's it. I don't see any questions coming in right now. I will stay maybe for 5 more minutes if there are some questions, but if there are no more questions, thank you for attending our seminar today. I hope, yeah, you learned something through the series. And currently, we are also having basic seminars for Asia, for Europe in the morning hours, in the European morning hours. So, however, starting, I think, in December or in January, the latest in January, we will have also again seminars in the American time zone, and also basic seminars again, and also on additional topics. Yeah, a lot of statistics. Here it's in the evening, so everybody is probably exhausted by now. So I don't see any questions coming in. Yeah, thank you again. Have a great day, have a great evening, and hope to see you somewhere, maybe in person. Thank you and goodbye.